Okay, this was the question asked in GATE 2016. The interesting point in this question is the excitation is usually we give positive sequence, but here the negative sequence has been applied, and the question is what is the phase difference between V capital AB, that means this line voltage, and V small AB, and this line voltage. So, what is the phase difference between these two line voltages from star to delta? You can observe this is in star connection and this is in delta connection. Okay, the phase winding equivalent diagram, I mean the three phase winding, this is equivalent to circuit diagram of three phase transformers. The circuit diagram is somehow draw like this. This phase mmf will be balanced by this phase in the secondary side. This phase mmf will be balanced by this phase because these two phases are somehow parallel. See, if you observe, this is in this direction, in the same direction this winding will be there. So our assumption is this phase mmf is balanced by this phase, and this B is somewhat horizontal, so this phase mmf will be balanced by this phase, and this phase mmf will be balanced by this phase. So to simplify this question, what I am going to do is, this ABC is a balanced supply but the negative sequence, that is if I consider this balanced supply as AS, this is BS, CS, that is A phase supply, B phase supply, C phase supply. How a negative sequence can be produced? A is given to A, sequence is produced by interchanging any two terminals. Now I am going to give B to C, not to B. This is the meaning of negative sequence. Now the sequence has been changed, C to B. Okay. Now if you draw this primary vectors like this, they will be star connected, so I am going to draw star equivalent. This is for simplicity I am going to put here A1 at the dotted side and A2, B1 at the dotted side, and this is B2, C1 at the dotted side, C1 at the dotted side, and this is C1 at the dotted side, and this is C2. So A2, B2, C2 are short circuited. So here the spatial vector notation will be, this is A1, if I take this as E1, this is A2. Here it would be C1 and this is C2. Why C1? Because it is a negative sequence. Achha. Now this is B1 and this is B2. So they are 120 degrees apart and they are balanced, and each vector length is same. I am not drawing exact lengths, but anyhow you might understand this all vector lengths are same. Now our now the game begins. Now our task is to find the line vector, because here line and phase vectors are same in delta. So what I am going to do is, as I have said earlier, this phase mmf is balanced by this phase mmf. So at the dotted terminals I would keep A1, small a1, and the undotted side I will keep B2. This phase mmf B will be balanced by this phase, so at the dotted side I will keep B1, at the undotted side I will keep B2, and this phase mmf is balanced by this C is balanced by this, so at the dotted side I will keep C1, and at the undotted side I will keep C2. So this winding vector and this winding vector will be in the same direction. Okay, now this small a1 a2 vector is in the same direction of capital A1 A2. Similarly, small c1 c2 vector will be in the same direction of capital C1 C2. Similarly, small b1 b2 vector is in the same direction of capital B1 B2 vector. Now you are going to connect these three vectors to form a delta. Now the interesting point will be, you have to note like this. See, if I take A1 A2 as a reference, now I am going to bluntly writing A1 A2. Okay, this is A1 A2. Now if you see this diagram, this is A1 A2, but A2 is shorted with B1. If you observe, because this is shorted, A2 and B1 are joined, so you have to join in the vector diagram as well. So A1 and B2, okay, you take B2 here and join like this. Sorry, A2 B1, A2 and B1 is joined, so A2 is fixed here. This is the reference vector, so A2 is fixed, so you have to keep A2 and B1 to join. So take this vector and place it here. In the same direction should not change, but vector can be spatially changed. Its direction should not be changed. So this is B1, A2 B1 as of circuit diagram. A2 B1 is joined. This is B1. Now B2, and here if you observe, B2 and C1 is joined. So take this C vector and this is B2, join with B2. This is now C1 and this is C2. If you observe here, A1 C2 are seems to be joined, you have this has to be satisfied in circuit diagram analysis. See here A1 and C2 are shorted. So this is the equivalent vector diagram in delta. Now make a fictitious centroid, because you have to compare two stars, you cannot compare star and delta. So you have to make it this balanced delta into balanced star. So I am taking this, this is like a triangle, I am taking a centroid. Now the output things are dotted. So A1, B1, C1 I assumed as dotted. So I will take this star equivalent with ones, C1. So it is C vector, small c vector, and this is B1. So this is small b vector, and this is A1. This is small a vector. Okay. Now he is asking small VAB vector. VAB is nothing but VA minus VB. So minus VB will be something like this. Minus VB will be something like this. So this is minus B1. VA minus VAB is nothing but VA minus VB. Okay. This is B vector minus B vector. Now its resultant would be somehow like this. That is, if you observe VAB, now here VAB will be, this is minus VB. So here VAB will be something like this. It is this is the reference. This is lagging by an angle 30 degrees. So small VAB is, capital VAB is lagging this reference by an angle 30 degrees. If you observe this vector, this is small VAB, it is actually coinciding with the reference what we have taken. If you keep this equivalent star at this side, the reference point and the small VAB vector will coincide. That is, small VAB lead capital VAB vector by 30 degrees. Okay. In other words, small VAB, capital VAB lags small VAB by 30 degrees. That is the point. So in while drawing this star delta vector, you have to be careful like this. Okay. Thank you.